And of course, right on cue, I don't know if you can hear that, but they started drilling up on my roof. But welcome, everyone. Thank you for dialing in. So today we have a different time than usual since our two presenters. I'm very glad they can join us. And Kay, Kristen, you're always welcome to call in going forward. Once a friend of Lunar Volatiles, always a friend of Lunar Volatiles. But yeah, so today we have Kay Wohlfarth and Kristen Wöhler from TU Dortmund, who will be talking to us about some of the work that they've been doing on modeling the thermal environment and its implications for analyzing surface hydration. And so Kay, Kristen, I will hand it over to you, and I will let you introduce yourself in more detail if you would like. So just a reminder to everyone, if you're not speaking, please keep yourself on mute. And Kay, I know you'll be going first, and then Kristen will be next. If people have questions, would you prefer if we wait until the end, or I know some people prefer if people ask during the presentation, but what would you prefer?
Maybe at the end of the chapter, so it's more like sub chapters, and wait for maybe the next slide and then ask the question.
Yep, sounds good. So so if people have questions, either hold on to them or feel free to put them in the chat, but I won't ask them until we've reached the end of a chapter. So with that, I will put myself on mute and I will hand it over to Kate.
Yeah, thank you very much for inviting me and Christian to the Friends of Lunar Volatiles group. Yeah, my name is Kai Wohlfarth. I'm a PhD student at TU Dortmund University. I'm currently in my last couple of months already writing the thesis and hope to hand it in this year. And earlier this year, I published a paper about thermal modeling of airless planetary bodies for Mercury and for the Moon, especially for spectral calibration for lunar hydration analysis. So the basic thing, why do we need thermal modeling? I think most people are aware of the reason why we do it. There is the strong absorption feature around 3 micrometer. That's diagnostic of the vibrational bands of hydroxyl and water. But the problem is, in this spectral range, the thermal emission that emerges from the lunar surface obscures this absorption feature, and the common solution is to employ a thermal model to perform thermal correction and to remove the excess radiation. But the crucial problem is that the results, especially the depth of the absorption feature, directly depend on the thermal model in use. And this naturally gives rise that we need to use accurate, or need to compute accurate thermal models to calibrate the data, such that we have a well-calibrated 3 micrometer absorption band that helps us to go on with the lunar hydroxyl and water analysis. Yeah, so that's a small picture of it. So the apparent this line is the apparent reflectance that was measured by the Cube instrument more than a decade ago, and with the form method from Wöhler et al. 2017, we could correct this thermal emission band. And now I reviewed the method that we did, and constructed a new, more detailed thermal model and extensively validated it. So this thermal model takes rough surfaces, realistic lunar statistics, and self-heating and self-scattering, which means that it also includes illumination and heating between small surface elements, which is a very important, which is another effect that determines the thermal environment. Came up with this model and validated it with with measurements from the Chinese weather satellite, the Gaofen 4 satellite, that was tilted by 180 degrees. And instead of observing the Earth's surface, it observed the moon and made really nice disk resolved measurements around 3.8 micrometers, so very close to the range of M cube or the upcoming Lunar Trailblazer instrument. And I validated it with a Diviner nadir, Diviner of nadir measurements in the range from 8 to 25 micrometers. And then the model has been validated, and I can finally use it to reprocess the M-cube images and come up with global M-cube lunar hydration maps. And the colors are basically band depth of the 3 micrometer feature. Yeah, the thermal model. So here I put in the reference. Wohlfarth et al. 2023 is a paper. I think it was also in the invitation to this meeting today. And the thermal model works like this. So first of all, I look at any position of the planet and consider small surface element and an illumination vector S, a view vector V, and a normal vector N. And this small surface element depends on longitude and latitude and the local topography. So then I take a small sample that is basically simulation of the roughness characteristics of the lunar regolith. It's a fractal I used a fractal landscape algorithm, and fractal landscape algorithm in this case means that my former colleague Arne Grumpe took the statistics from the Shepard and Helfenstein paper, where they meticulously analyzed the statistics of lunar regolith fractal dimensions and constrained the fractal surface generation algorithm with the statistics from Shepard and Helfenstein. And this gives an algorithm that outputs fractal surfaces, and you can generate tons of different different random fractals that behave like the moon does. Then you can zoom in and see those small patches, or the small pixels. And for each pixel, I computed the following. So there is the sun that illuminates each pixel and heats the pixel. Then the pixel scatter light to the pixels nearby and emit thermal radiation so that they heat the other pixels. That is called self-scattering and self-heating. That's a very intricate problem where you need a gigantic matrix that basically connects all pixels together. And then I computed the thermal emission that emerges from the surface and implemented a couple of ray traces to get the geometry and the illumination and the viewing conditions right. And that's then I sum it up, project the thermal emission, and then associate the then say that the initial pixel on the lunar surface over here is just associated with one thermal emission curve. That's the superposition of the temperatures of all of these fractal pixels over here. That's the thermal model. Used tons of numerical stuff and large computer to make it really fast. So this surface element has 200 times 200 pixel, in total 40,000 pixel. and I can run a lunar surface with maybe 300,000 or 400,000 pixels, where each of these pixels is associated with another 40,000 pixels in a couple of hours. So it's extremely fast because of the ray tracing implementation and that stuff. And you can manage to, compute the thermal emission of a rough lunar topography in a reasonable time. And what I'd like to point out are the effects that come from the surface roughness. And for this, we can take a look at this configuration where the spacecraft is in nadir position. So this is one of these fractal surfaces that I computed yesterday afternoon, and the emission angle is 0, so the spacecraft is in nadir position. The sun illuminates the surface from the side and can vary between 0 and 90 degree, and the azimuth angle is not that important here, but it is 0 degree. Now I assume that this fractal surface is 1 astronomical unit away from the sun, so basically as far away as the moon usually is, and compute the temperatures of all the single pixels of the surface element, and then we get this top view. So this is a map of the surface, and red means we have pixels that are around 400, almost 400 Kelvin, and directly illuminated from the top. So that's the top view of this fractal surface for 0 degree incidence angle. If the sun sets maybe to 40 degree incidence angle, we already see that the temperatures become colder because some parts of the surface are tilted away from the sun. The local incidence angle on the surface is not so small anymore. So there are regions that tend to get a little colder, and we can increase the incidence angle and proceed with it, and we can see that the surface becomes colder and colder and colder to 85 degree. But because of this rough surface structure, we still have some regions that are hotter than other parts of the surface, and this gives rise to a couple of interesting effects. The second thing that I plot is the temperature map of the local surface that is visible at the detector, and in the nadir case, because the spacecraft looks from above, we simply see every pixel, so both so everything is the same. And now we take the temperatures of one of these pixels, compute the Planck function, the thermal emission curve, and sum it up and project it so that we get the thermal emission as seen by the detector. And in this case, we simply between 2 and 3 micrometer, we simply get this increasing line that is the radiance, the thermal emission for unit emissivity, given this configuration, simply summing over the Planck emission functions of all single pixels. Then, when considering maybe 40 degree, we see that there are some parts that are colder. The thermal emission curve is flatter, and the superposition of all thermal emission curves is even flatter, and we can see that the thermal emission for 40 degree is significantly below the other line. And when we consider maybe 70 degree, it gets even colder. The Planck functions on average get smaller, and we get this thermal emission. And what's really interesting to see is when we compare it to a smooth surface. So I calculated the same thing, but I didn't assume a fractal rough surface, but a smooth surface, which and the results are indicated by the blue lines. This has some very interesting properties. So for an incidence angle that is 0, so in nadir configuration, everything, so the blue and the red line are almost the same within numerical accuracy. For 40 degree, we can already see that the thermal emission of the rough surface in red is approximately 10 to 15% higher than for the smooth model. And for 70 degree incidence angle, we can see that it's maybe 3 times hotter. Not really hot, but the thermal emission is 3 times higher than for the smooth surface. So the higher the incidence angle gets, the lower the thermal emission becomes. But the higher the incidence angle gets, the difference between the smooth and the rough model, the relative difference becomes larger. And that's the first thing that happens due to surface roughness. But the geometries can be more complicated, and I have this case number 2. It's not really complicated, but it's a different geometry where the spacecraft and the sun basically look into the same directions, and I computed the same thing. I moved the sun and the spacecraft around, assumed that the emission and the incidence angle are the same, so it's basically some opposition configuration, and we see that the temperature of the maps of the surface change as they did before, but the temperature distribution that is visible at the detector changes because the spacecraft now sees the surface under some emission angle E, and because of shadowing, it cannot see all the surface elements above maybe 50 or 60 degree. And in this map, I set every pixel to black that cannot be seen by the detector under this configuration. And when we compute the thermal emission curves, again in red, we see that in general the effect is the same, but now the difference of the thermal emission with respect to the smooth surface are higher compared with the previous case. So if I go back to the previous slide and forth, you can see that the red curves in for 40 and 70 degrees are significantly higher in the opposition configuration. And this is just because we see pixels that are on average hotter than for the Nadia case. Now I have a third case where there is a azimuth of 180 degrees between the incidence and the emission. And what we can see here in the map, that the temperature map that is visible at the detector is, that we have lots of blue regions over here. So we are somehow somewhat looking from behind at the surface, and we see more regions that are in shadow, that are really cold, and we collect Planck functions that are colder, which leads to the effect that the red and the blue curve, the rough and the smooth model, are somewhat similar. And when we look at 70 degree, I should have included a zoom opportunity, then the smooth model is even above the rough model. So when we look from behind, we see the shadows and everything gets colder. And when I quickly change between the slides, you can see that depending on the geometry, whether it's not an idea or opposition, or this case number 3, the thermal emission curve changes. And what I would like to highlight is that surface roughness is a really important thing, because depending on the exact configuration of the sun and the space probe, we see quite different results. And because they are important, I use them to reprocess the M-cube data set. But first of all, we need to make sure that the model somehow describes what is really going on in the real world. And for this purpose, I took these two data sets. On the one hand, the Gaufing 4 data set from Wu 2021, and the Diviner data set from Benfield's great paper from 2015 that included a thermal model that also already had roughness with those bow-shaped craters. So this is the measurement of the taken at the 30th of July 2018 from Wu and colleagues, which shows the lunar surface at 3.7 micrometers, because it's in the infrared region, which is not real thermal infrared, but already beyond the near infrared in some sense. Mare and highland regions are inverted. So in this case, the highlands appear, the Mare appear brighter and the highlands appear darker. And at 3.7 micron, still 10% of light, of reflected light are left, but there's almost 90% of thermal emission. And what I did now is trying to reproduce these measurements using a reflectance model and the thermal roughness model to study the roughness effects and validate it. For the reflectance model, I used the Happy model because it's very well constrained for the lunar surface, and I derived the emissivity from the directional hemispherical integrated reflectance. The surface albedo is given by this integral. It's the directional hemispherical, the bolometric directional hemispherical albedo, which is the albedo that's necessary for thermal computation. Sometimes in the literature it's just a fixed number, but the true physical quantity depends on the incidence angle. I think there's a paper from Vasavada 2012 that derived the directional hemispherical albedo from Diviner measurements, and from Skuratov 2011 you can also find the definition of the directional hemispherical reflectance. I used the M-cube global data set to compute the single scattering albedo, and then I took the Apollo samples from the RELAB laboratory to extrapolate from the 2.5 micrometer single scattering albedo to 3.7 micrometers with a single scattering albedo at 3.7 micrometer. And it turns out that there is a linear relationship with a correlation coefficient almost close to 1. So it's a very stable relationship, and I'm quite confident about this extrapolation to get the single scattering albedo route. I combined everything, computed the reflected light for the entire disk, the thermal emission, and the thermal roughness model, plugged everything together and ran it for different roughness values from 10 to 40 degree average roughness angle, and determined the best fit that best describes the data. What turns out, it turns out to be quite, so there seems to be quite some resemblance between our modeling result on the right and measurements from Wu et al. 2018. We found that value close to 23 degree average roughness value best fits the data. And the first visual impression shows that they look quite similar, but when you analyze it a little bit more in detail, the ejector blankets here around Copernicus are not perfect, and maybe the contrast between Mare and highland could be a little bit higher, but I'll dig into the details by simply cutting out profiles and looking what's going on. So the first profile runs from west to east in the south of the visible hemisphere, mainly to highland, and the data points are in white. The smooth model is in blue, and the rough model is in red. And when we zoom in, we can see that the rough model almost perfectly agrees with the data points, and these spikes are mainly due to topography. So this the spikes come from all these small craters, and I included the DTM of the lunar surface to somehow model these effects. And what I'd like to highlight is that moving from the smooth model to the rough model and fitting the data just requires one parameter, and this one parameter is the average roughness, which turns out to be close to 23 degrees. So with one parameter, we can shift the thermal emission curve to match the data, and of course external constraints from M cube and to get the local albedo right. Then I looked at this profile. Blue is the smooth model, white are the points, the data points. Red is the rough model, and we can see that it describes the data quite well, except for this region here, which corresponds to the ejector blanket of Copernicus. In this case, the model somehow overestimates the thermal emission. Probably this is due to the fact that the ejector blanket is not correctly captured in the albedo data. This would explain why the entire curve, also the smooth curve, is shifted with respect to the data. This profile is also really interesting. So in this here we can see that using a higher roughness shifts our curve to the data points, and these small craters are also well reproduced, but there seems to be some offset over here, which can be found in Oceanus procellarum, and this region is particularly high in Titan. So there seems to be some mismatch between the data and the model in Titan-rich regions, and my guess is that Titan-rich Mare regions are really, really dark, so they tend to become a little hotter. And I used the Apollo samples to extrapolate between the to extrapolate between the 2.5 micrometer albedo to 2.8 micrometer, and probably this was not perfect at this point. It needs some revision, but it works well for all the other spots of the surface. Some questions in the chat. Titanium. Yes, that's titanium. Probably there was so in German it's called Titan, and probably I got this vocabulary wrong. It's titanium. Yes. Then let's look at the diviner instrument. So the diviner instrument performed these EPF measurements. So the diviner has an azimuthal mount and can change the inclination with respect to the surface. And the red line on the left is the diviner footprint. The black lines is the pointing of the diviner instrument, and on the right you can see the configuration of incidence angle in red, emission angle in blue, and azimuth angle in black during this EPF measurement. And this contains a lot of different orientations, and this was a great opportunity to validate the model for slightly higher wavelengths. So we have the maneuver, the maneuver of the diviner instrument, and on the right, the red dots that are the brightness temperatures at channel 4, around 8 micrometers, and the green dots are the brightness temperatures of the at channel number 7 that extend up to 25 micrometers. The black line and the blue line, that is are the modeling results, and we can see that both lines agree with the data points. So the thermal model is able to reproduce the brightness temperatures of Diviner during this very intricate EPF maneuver. Something is really nice to see here. So the first half of the maneuver, first 40%, we have an azimuth angle around 110 degrees. So the sun looks slightly more from behind, sees more shadows, and here we have more like 60 degrees, and we see more of the surface parts that are illuminated, and this directly translates into we see more parts that are illuminated for higher brightness temperatures, and we see more shadows at colder brightness temperatures. I run this for all EPF maneuvers in the Benfield 2015 paper, and found that the roughness values between the channel 4 and channel 7 are largely consistent. But something is really interesting, and this is in a result that has also been found by Benfield, which is that there seems to be some roughness difference between the EPF maneuvers and the Nadia measurements. So I tried to model them as well, and found that the Nadia measurements over a lunar day tend to agree more with 20 degree of surface roughness. That's something that I discussed here. So this is a cube which gives us the incidence angle, the emission angle, and the azimuth. And all these colorful points describe the geometry of one of the measurements. So Diviner Nadia is more like 20 is here. So we have zero emission angle and almost different set of incidence and azimuth angles. We have the M-cube measurements. In black, that's Gauffin 4, and in red are the Diviner EPF measurements. And these measurements here tend to be more consistent with 20 degrees. So the M-cube is sandwiched between the Diviner measurement with best fit around 20-degree roughness, and the Gauffin 4 data in black is around 21 to 23, and the black points also extend into this direction. And M-cube seems to be sandwiched between these two data sets. So I derived also, so I just assumed to take 22 degree of average surface roughness to process Diviner. But the EPF measurements to process M-cube, sorry, but the Diviner EPF measurements are somewhere up here, so they're quite far away in this configuration space, but need higher and are in a different wavelength region and need slightly higher roughness values. And that's something I'd like to analyze in the future with more Diviner measurements potentially, because that's something effect that is not yet understood and is reproduced by the entire class of these thermal models. So because 20 degree is good for this region, and 20 degrees is also good for that region, and M-cube data is sandwiched in between, I just assumed the average, which is 22 degree of roughness, and reprocessed the entire M-cube data set. This is found at Zenodo, so I uploaded it. So whoever is interested to work with it, that's the Zenodo link, and reprocess the maps from 2017 2019. They slightly underestimated the roughness, but now I'm pretty confident that they must be around 20 degree for the M-cube geometry and the M-cube wavelength region. and that's what we get. So this is the lunar near side, the lunar morning, and the blue color is basically the relative band depth of the 3 micrometer band. So blue means a deep band, red means almost no band, and it's a relative band. So this is in percent. In the lunar morning, it's very blue, so we have a deep band. In lunar midday, it becomes the feature becomes flatter, and also in the Mare regions it seems to become really dry, and in the lunar evening everything is seems to be we seem to get deeper bands again, which agrees with lots of other studies in this field, but now with a new thermal calibration. When we look at the lunar far side, we can see the same effect. In the lunar morning, there are deep bands. On lunar midday, they become a little shallow, and lunar evening, the bands get deeper again. And what's also nice to see is that there seems to be some effect with latitude. So the higher the latitude, the deeper the band depth is. That's also something that's really interesting. So to sum it up, there's a new thermal roughness model with high throughput, lots of numerical methods inside. I validated it with the Gaufing 4 and Diviner data set. Turns out to be quite nice, and reprocessed the Cube data set to see reveal this band once more. But probably there is something at higher wavelength in more extreme configurations that one needs to look into, which are these EPF measurements of Diviner. Yeah, that's my talk, my part of the talk, and I think I'm open for questions, but I will also hand over to Christian shortly afterwards, who will talk about the modeling of lunar hydroxyl based on the data set.
All right, thanks, thanks, Kai. So I think what we'll do, maybe we'll take 5 minutes for questions and then hand over to Christian. And in case, so our official end time is 1 p.m. Eastern. In case we go over, I understand if people have to drop off, but I will record this and I'll share the recording afterwards. So if you have to drop off at 1, don't worry, we'll just, we'll just share the recording. But okay, so we have one question in the chat from Stefano Bertoni, who asks, when you talk about rough or smooth, what baselines or resolutions are you considering?
So for the smooth model, I say smooth is flat. So there is no need for a baseline because it's simply a flat surface. And rough, I derived it from the Shepard and Helfenstein paper from 1991, and there's a plot, and I think there's also a similar plot in Rubanenko 2020 or 2021, where we have different scales of the surface from sub-millimeter region up to a couple of centimeters, and some statistic that describes the roughness angle, the average roughness angle at different resolutions. And I took the same geometry, took the same statistics, constrained the fractal surface with it, and the theta bar, this value is measured at the thermal isolation scale. So it's basically the roughness at the smallest scale where the adjacent surface facets are still thermally isolated. So the scale is not has been constrained in Benfield 2015 and Grumpe and Wöhler 2019. It's believed to be somewhere around 1 millimeter and above, but it's somewhere in this this region. Yeah.
And I guess related question, Kai. So what is the pixel size or the smallest pixel size in your model?
The smallest pixel size is 1 millimeter, but there's one thing that's really interesting. So we can go to the equations. So, we can go to the equation. I need to find this one here. The equation. So that's from in my paper. And when you look at the self-heating and self-scattering factors, here Vm is the size of the pixel, and that's the distance between adjacent pixels. And when we assume 1 millimeter, it simply cancels out. And that's one funny property, because the actual scale cancels out, so we don't need to worry anymore. And then scales are not so important.
Interesting. And Stefano has a follow-up in the chat. And Stefano, do you want to unmute? And I can read the question, but if you want to unmute and read the question yourself, feel free.
Hey, hi. Yeah, I can. I just had someone else in the same room. Yeah, no. Thanks for the answer. I was just wondering then if you would know what's the impact of all these roughnesses at different scales. Like is meter level roughness, introducing meter level roughness in the models, would that be sufficient, and at what level to get a good fit of the data? Or do we really need centimeter or millimeter roughness, which cannot really be constrained by altimetry or imagery even on the moon?
I can go to one of these slides here. I have, let's call it roughness on larger scales induced by the topography, and the smooth model in blue already has the topography, so it models these spikes. But
yeah, exactly. That's why I was wondering when you mentioned that the smooth really meant smooth. I was a bit confused because there you already had topography, and I didn't know which kind of topography you used, which resolution, etc.
But following your question, so small scale roughness on the centimeter millimeter level is vital, because you needed to lift the entire thing. So moving from the blue line to the red line requires small scale roughness, and that's really important. Otherwise, you get very weird effects. It's important to in the morning when you have very oblique illumination of the surface. It's important in different latitudes. So on larger scales, it is good for retracing these topographic effects, and it will, when zooming in, it makes everything more accurate. But the small scale roughness from millimeters to centimeters is really the thing to make the model fit. So it's vital.
Great, thank you.
All right, so let's move on to Christian. But if people have more questions, feel free to put them in the chat. And in case anyone has to leave for lunch or another meeting before we get to the questions, we will record them. So even if you have questions and have to leave, feel free to put them in the chat, and we'll get to as many as we can. But yeah, thanks Kai. And it's a really beautiful model. Like it's nice to see the results. And yeah, we will hand it over to Christian.
Okay, hello, and thank you for the invitation, Herbati, to give a talk here. My name is Christian Wöhler. I'm leading the image analysis group at Technical University of Dortmund, And yeah, we are already working in our group on lunar volatiles, especially lunar hydration on the lunar surface for, well, 10 years now. And yeah, Kai just presented our most recent results on the thermal modeling, and I will give an overview of our works, the works in our group about a physical simulation of lunar hydration, which means yeah, lunar hydration on in the illuminated parts of the lunar surface. So I will not refer to how can I? Yeah. I will not refer to permanently shadowed regions near the poles, but to the illuminated lunar surface at all latitudes where solar illumination is relevant. And yeah, one important point is the time of day dependent variation of superficial hydration or superficial OH H2O content, as I would put it. And yeah, very early descriptions of 3 micron band depth variations depending on the lunar time of day were already published by Sunshine et al. In 2009, based on it was Cassini-Wims data, and also by McCord and others in 2011 based on M-Cube data. The finding by Sunshine was mainly that there was that hydration was stronger in the lunar morning than on midday, and in the afternoon it was again stronger than at midday too. McCord et al. Found that the 3 micron band depth was strictly correlated with the degree of illumination, but in that paper no removal of thermal emission has been done yet. So yeah, and I have not cited here the paper by Peters et al. In 2009, looking at M-Cube data, because there no time of day dependent variations were considered. It was just about the latitudinal variations and variations, yeah, mainly with latitude. And one of the works that came sometime afterwards was Lee and Millikan, who found the strongest time of day dependent 3 micron band depth variations at mid latitudes. But their method for thermal emission was not physically based, but was statistically based. So statistically means that certain shape of the average lunar near-infrared reflectance spectrum has been assumed, and it's not totally clear what happens if the actual spectrum deviates from those statistically derived mean, from the statistically derived average behavior. In our group, we had a publication also in 2017, and now Kai Wohlfarth's current publication, where we found that time of day dependent variations of the 3 micron band depth increase with latitude. And there is, on top of that, a significant 3 micron band depth at midday, even under full illumination, at all latitudes, even at the equator. And in quite a similar way, Banfield and others found significant 3 micron band everywhere on the moon at all times of day, with some weak time of day dependent variations if one looks closely into their data. But one must say only one location was really examined in detail with respect to time of day dependence. And which I did not include here because I just forgot it, there were the works by Honeyball et al., is also present here, who found on the one hand water in the sense of H2O on the moon, but who also found diurnal variations of the 3 micron band depth based on ground-based telescopic data acquired with the SPECS instrument on the IRTF facility on Hawaii. Okay, so this is just an overview of the current and past findings in the behavior, especially time of day dependent behavior of superficial lunar hydration. Our global maps of the 3 micron band depth, which I have called OH-IBD, so OH integrated band depth maps. The main results are in the lunar morning, we have that the band depth in the polar highlands is higher by about 20 to 30% than in the equatorial highlands. There is a clearly non-zero highland level near the equator in the morning, and the Mare OH-IBD is lower by 10 to 15% than in the equatorial highlands, which might have changed according to Kai's new findings he just presented, because there in the morning the Maria were a bit more intense regarding their 3 micron band depth. So that, of course, this apparent contradiction is due to the fact that these results were derived from our older thermal model, which has been refined by Kai. But in principle, for what I will show today, that doesn't make a real, for the modeling, that doesn't make a huge difference, so rather insignificantly. And that has not changed in comparison to the most recent version of the thermal modeling. The lowest 3 micron band depth values were obtained for high titanium Mare basalts. At lunar midday, there is no or very weak latitude dependence of the 3 micron band depth. The level in equatorial highlands is just maybe 10–15% lower than in the morning, and there are near zero values in the Maria, in some Maria, especially in the high titanium Maria. And the lunar afternoon, the level is basically back to the morning value, a little bit below, one must say. So it's not totally symmetric across the lunar day. And the Mare, as it's written here, the Mare band depth is higher than at midday in the afternoon, but about maybe 20% lower than in the morning. So this asymmetry has also must be reproduced by any kind of modeling. And here, just as an illustration, here the difference between morning and midday 3 micron band depth can be taken as a measure for the amount of the solar wind-induced hydroxyl water component, because the diurnal changes with time of day are most likely due to changes of the flux of solar wind protons, hydrogen atoms without electrons basically, which can react with oxygen in the lunar surface material to form OH and or H2O, and H2O, because H2O has been detected by Hannibal et al. Then the question is there a second more stable OH-H2O component? Then let's look at models by others. There is a model by Farrell et al., published in 2 stages in 2015 and 2017, which predicts a decay of the hydrogen concentration by at least 1 order of magnitude from lunar morning to lunar midday at moderate latitudes. Why only H? Because they only simulated hydrogen and not hydroxyl. And in our own model predicts realistic values for the timescales of OH diffusive loss evaporation, and also for photolysis, that predicts a decay of the OH concentration by at least, again, an order of magnitude from lunar morning to midday. This is not what we observe, though. So our observations at lunar midday indicate a significant 3 micron band even at low latitudes. There is no decrease between morning and midday of 1 order of magnitude. That has been reported by us in 2017, now by Kai in his recent paper, and it has also been confirmed by Banfield et al. And this, in principle, can be explained by the presence of a more strongly bounded hydroxyl or water component, which has already been suggested by Klima et al. In 2013, which would then have to be stable against diffusive loss, evaporation, and photolysis. Photolysis is the same as photodissociation. And this component would then add up with the time of day dependent component. Then we can get the observed 3 micron band behavior. Okay. Now the question is, which processes govern the abundance of sufficient hydrogen and hydroxyl? Here in this model, I will only talk about hydrogen and hydroxyl, not water, because the reaction of hydroxyl to water involves a variety of physical parameters which are not well constrained. So one can actually produce any kind of result if one extended that the model towards H2O. So that we have not yet done that. I don't want to say it's not possible or but we haven't done that. So I'm just talking about hydrogen and hydroxyl. There are competing processes, that is source processes and sink processes. First of all, there is the adsorption or maybe implantation better of protons H+ from the solar wind. That has already been suggested in the famous paper by Starochina et al. In 2001. And even in the 1960s already. I think Starochina was not the first to propose this mechanism. The first were US scientists in the early 1960s before the Apollo missions. Then there clearly is the delivery of hydroxyl and H2O by micrometeoroids. There is a steady stream of micrometeoroids onto the lunar surface, and many of those micrometeoroids are chondritic and contain hydroxyl and water. Then, as a source process, another source process is the reaction of hydrogen with oxygen from the surface material to form hydroxyl. That has been assumed by Farrell et al. 2015, for example. And then there is the temperature-dependent diffusion of hydrogen and hydroxyl, again suggested by Farrell and others. Then there is another, as we found, rather important mechanism, namely the solar flux-dependent photolysis, photodissociation of hydroxyl, which has not been taken into account in too many models. Mitchell et al. Was the first paper to consider this mechanism as an important process, but they didn't combine it with other processes and to see which one is stronger. And then there is another destruction or sink process, namely the sputtering of H from the lunar surface, which was mentioned by Farrell et al. In their 2015 paper, and of course also sputtering of hydroxyl, which was analyzed in detail by Woods et al. 27 and 2010. All in all, our model consists of a set of coupled ordinary differential equations describing the dynamical behavior of the hydrogen and hydroxyl column densities. That has been published in detail in 2019 by my previous postdoc Arne Grumpel and me, basically, and Alexei Bereshnoi. Yeah, so I don't state all these equations because I think it's sufficient to state the processes. And yeah, one important aspect is that, for example, the diffusion very strongly depends on the temperature. So it depends on the exponential of the inverse absolute temperature. It's a very strong temperature dependence. This is not true for the photodissociation, and also the reaction rate between hydrogen and oxygen is strongly dependent on the surface temperature. So surface temperature plays a crucial role because the Arrhenius law, which governs such processes, has an exponential dependence on temperature. And what we also did was to adapt the physical model parameters, in particular the hydrogen activation energy and the hydroxyl photolysis time, to the M-cube observations. The other physical parameters could be constrained from the literature to a degree that we could show that variations by an order of magnitude have no visible effect on the model output. That was only not true for the hydrogen activation energy. There was no real information in the literature, and also the hydroxyl photolysis time, the characteristic time of hydroxyl photodissociation, was only given for the hydroxyl gas phase, which we then used as a lower limit. So we tried to depict this here, these processes. So implantation of solar wind protons means we have protons here, and this is the flux of the solar wind. That is, we have hydrogen implanted into the surface, which may diffuse to the surface and evaporate. There is a characteristic implantation depth. The H can react with O to OH with a certain probability. For that purpose, of course, free oxygen must be available, and which can be set free by also by ultraviolet radiation of the sun, for example. And also the OH can evaporate or diffuse to the surface. It can photodissociate, then a certain part of the hydrogen may return to the surface and be available for reactions with O again. So, and you can imagine that this is quite a complicated mixture of competing processes, one of which increases the level of OH, the other one decreases it, and that's why the formulation as a system of coupled differential equations might be appropriate. And on top of that comes the delivery of hydroxyl and water by micrometeoroids. So water by micrometeoroids can also decay by photodissociation. Also, it can return to the surface, it can evaporate after the impact, and it can decay into various species, namely H+, or hydrogen, or H2, or here hydroxyl, OH+, and electrons, free electrons. So there are various species into which the H2O can decay, and the tau factors always denote characteristic timescales, and of course also the micrometeoroid delivered hydroxyl can also decay into various species like H, O, OH plus, and free electrons, and then again evaporate and return, and can of course also photodissociate. This is all quite complicated, so yeah, I will talk about that later on, how we tackled this complexity of this part of the model. Actually, we did it in a rather brutal way. Okay, so what are the modeling results at first of all, at high latitude? Here, in the first approach, smooth surface is assumed. So there is no surface roughness yet. That will come later. But here in these results, there is no surface roughness yet, only smooth surface. And we can see here that, yeah, we can see that here we have the different colors here denote the photolysis time. And given a specific photolysis time, the best fit of the model, no, the hydrogen activation energy is estimated by adapting the model to the data, given a certain value of the photolysis time. The minimum value is 5 by 10 to the 4 seconds, which is the gas phase photolysis time of hydroxyl given by Hübner and Mukherjee in the 2013 overview paper. And yeah, so this is here these are the corresponding column densities, which we have converted to the OH mass fraction in ppm by assuming an implantation depth of 100 nanometer as given in the Farrell papers. So in that way, column density can be converted to OH mass fraction. So this is 10, this is 100 ppm. And what we get here is about at most 20, rather less than 10 ppm OH mass fraction. And here, this is a comparison of of our data, the M-cube data, compared with the modeling results for the orange curve here. And of course, we have to take into account that M-cube doesn't measure any kind of mass fraction or column density, but only relative band depth. So we just assumed that the relative band depth that we observe in the M-cube spectra is proportional to the OH column density. And we estimated the proportionality factor along with the physical parameters. In that way, we can translate M-cube measurements to column densities, which are here, of course, of the order less than 10 to the 17. This is how it looks like. The interesting thing is if we switch off photolysis here, or use a very long photolysis time, so 100 times larger than the gas phase value, we get a high but constant, more or less constant OH column density. So it's the photodissociation which primarily produces, at least at high latitudes, produces the time of day dependent variations. It's not so much the diffusion or the evaporation due to the thermal evaporation. And even at low latitudes here, 33 degrees south, without photolysis, we have again a more or less constant value. And with photolysis, we obtain the, the time of day dependent behavior that we observe in the M-cube spectrum. And here stable component has been added as a simple offset, because the stable component is assumed to be insensitive to photolysis and evaporation. This stable component, according to our modeling, seems to have kind of latitudinal dependence. So it's strongest near the equator, whereas at the high latitudes, hardly any of this stable component is required to explain the observations. This might be explained by the different, the stable component is not necessarily an internal component. So it doesn't necessarily mean that it's magmatic water or something. It might also be due to OH that diffuses into strongly bounded binding states of the surface minerals, and such strongly bounded binding states with binding energies of more than 2 or 3 electron volts have indeed been described in the literature. So that can happen, and the flux, the flux of the solar wind is less in the high latitudes, which might explain this decrease towards the high latitudes. Would be a possible explanation, at least. Okay. And here the actually relevant points here are the orange ones with the photolysis time of 1.5 times 10 to the 5 seconds here. The orange, that's the value we found to be best consistent with our data. Or let's take this as an upper limit and the gas phase value as a lower limit. So then we get this here. So there is a more or less steady decrease of the component of this so strongly bounded component with latitude, with increasing latitude. Okay, now the question, what about the micrometeoroids? We simulated all these processes in a similar, in a separate system of differential equations. And we found that the column density of OH delivered to the lunar surface and undergoing the destruction processes that I've already described, leads to a column density that is about 1 order of magnitude lower, at least an order of magnitude lower than the OH component due to protons implanted from the solar wind. And then we simply omitted this micrometeoroid delivered component because, as I said, it's an order of magnitude lower than the solar wind induced component, and one could model this in more detail, but the measurement accuracy of the M-cube data are not at all, by far not high enough to be able to verify anything of it. We only took into account sporadic micrometeoroids, but we also simulated more or less for fun the effect of a several hours meteor shower, but that just brings some local increase, and the amount of OH set free in that way or is much too low to find it in M-cube data. Maybe with trailblazer data, one should look at the moon during meteor showers and see if there's an increase in OH or H2O or H2O signature. Might be the case. Depends on the possible measurement accuracy. Okay, and now I will mention very shortly, very briefly, our first results regarding hydroxyl on a rough regolith surface. This has not yet been published as a full paper, but only as a LPSC abstract. So what we did was to take one of Kai's fractal surfaces, which has an extension of 200 by 200 millimeters. With his model, we heated the surface according to the solar illumination in the course of the lunar day at different latitudes. So we always took the same piece of surface for this experiment, but assumed different latitudes. And we simply let the model run for independently for each pixel, because each pixel has a different temperature. And this is what we get in the morning at 7:30 a.m. This is rather an overlay of the column density map on the rendered view of the rough surface. And at 15 degrees latitude, actually, most just a little bit of most of the solar wind induced OH disappears by midday. Of course, there's still the stable component left, which is not considered here. And then in the afternoon, the hydration comes back. And the hydration is, at 15 degrees latitude, there are no micro-cold traps. So there are no roughness structures which are always cold due to lack of illumination. That doesn't exist at this latitude. But here at 45 degrees, such areas begin to come up. And the finding is that the hydration, not surprisingly, is always strongest around such permanently shaded areas, just because the surface is on the average coolest around them. That is at 45 degrees latitude, there are some high OH concentrations in segments of the surface that are tilted away from the sun. Permanently shadowed regions are not considered here, so they are simply blanked out and not simulated, which is visible here at 75 degree latitude. There are a lot of small scale areas which are never illuminated during the day. And of course, OH can pile up in these areas, but since they are not illuminated, they can also not be detected spectrally. So we simply discarded them. But around those micro cold traps, which we see here, we see high concentrations of OH. And at midday, we also see basically nothing in the areas tilted towards the sun. In the evening, the hydration comes back. During the night, nothing happens, and then the whole cycle begins again. Just as a comparison, smooth versus rough surface, we can see that here mean means mean OH column density for the surface segment converted to column density in meter to the -2. So this is rough surface, and the dashed lines are smooth surface. And at low latitudes, smooth and rough surface are on the average not too different. So solid and dashed line are nearly the same. Also at 45 degrees, the amplitude, the diurnal amplitude of the smooth surface is stronger than for the rough surface. And at 75 degree, we see that the average column density on the rough surface is nearly constant, whereas there was a slight variation for the smooth surface. And now the right diagram distinguishes between those locations here, 1 and 2. 1 is a location that is preferentially tilted towards the sun at all latitudes, and 2 is a flat part of the surface. Here we can see, okay, at near the equator, there is no big difference between the two locations. Solid line is always location 1, so the warmer location, and dashed line is no, location one was the warmer location. Yeah, location one was the warmer location, and here at 45 degrees there is a difference, and the difference becomes even very large, more than 2 orders of magnitude for high latitudes. So these are some interesting effects that we still need to analyze further and disentangle a bit. Here on the right hand side you can see that it more or less fits with the measurements. The dashed lines is the offset. Symbols denote the observations. At high latitudes the consistency is not really perfect, but for low and mid latitudes it sort of works. And the dashed lines denote the stable offset, which is smaller at high latitudes than near the equator. So at 45 degree latitude, there is still hardly any difference to the equator, and then suddenly this stable component drops off. It's not clear if that's really real or not. On the left-hand side, you can see a movie, how the simulated OH column density behaves on a rough regolith surface at 45 degrees latitude. Now is afternoon, sun goes down in the west, you see the shadows, and then comes the night, and now it begins at the morning, shadows disappear, and a bit of in the early morning OH is built up, and then it's destroyed by increasing temperature and photolysis. Yeah. And at midday, it's more or less, well, not completely, but to a high extent destroyed. And then the hydration comes back in the lunar afternoon, but please don't believe too much of this. This is ongoing work, and we are currently examining this in more detail. Okay, so what are the main results of our modeling studies? First of all, realistic results were obtained for photolysis times up to 3 times higher than the gas phase photolysis time. Plausible gas phase is minimum, and a few times higher because photolysis might be more difficult for implanted hydroxyl than for freely floating gas phase hydroxyl. Without photolysis, the OH column density would be nearly constant. So we need photolysis to explain diurnal changes. Only a negligible fraction of superficial hydroxyl is removed by sputtering. That is something we examined in detail. Sputtering rate is several orders of magnitude lower than evaporation rate and photolysis rate. The amount of micrometeoroid-delivered hydroxyl and water is about an order of magnitude smaller than the amount of solar wind implanted hydroxyl. Okay. So we neglected it, which is maybe not the finest way to get rid of the problem, but otherwise everything would have become extremely complicated. The strongly bounded hydroxyl component is not necessarily endogenous or magmatic water kind of thing, but may also be due to slow diffusion of solar wind-induced hydroxyl to depths that are inaccessible for ultraviolet photons from the sun and into binding states of higher energy, counteracted, of course, by sputtering. So, So sputtering might remove that component so that it doesn't accumulate, but achieves some sort of equilibrium and limiting the amount of this stable component. The surface roughness changes the mean hydroxyl column density only insignificantly, but the distribution of OH on a rough surface is strongly non-uniform. That's the influence that we could identify for the surface roughness so far, but that's ongoing work. Okay, So that was it from my side. Thank you very much. Are there questions?
Thanks, Christian. That was great. And yeah, we'll hold a few minutes for questions. So feel free to raise a hand or put something in the chat. While folks are thinking of questions, I have a few. So regarding the first 2 points on your on the slide that you have, so does the model make any assumptions about about where the photolysis occurs? Like, is this OH radicals just being dissociated while they're in flight, or is this photolysis of OH that is absorbed to the surface and within reach? Like, does the model make an assumption about that?
This is an average over everything. So
Okay.
both in the surface material and during possible ballistic flights, where it's not clear if ballistic flights over great distances really occur. So this is a point that to me seems to be still under debate in the literature. So it mostly refers to OH implanted into the lunar surface material, and which fits with our finding that the best fit of the model with the observations occurs for photolysis times which are significantly longer than the gas phase photolysis time.
Okay. And Carly Peters has a question in the chat. And Carly asks, what does happen during the night? And
in our
Carly,
model,
if you wanted to expand on that.
In our model, just let me think, nothing, but only delivery of hydroxyl and water by micrometeoroids. So in the night, there is a steady stream of, assumed to be a steady stream of hydroxyl and water by micrometeoroids. But if hydroxyl has accumulated at some points on the surface, it will not disappear during the night. That's basically what happens during the night.
So I presume that's because it's too cold?
Yes, exactly, because the processes that we look at, which is thermal evaporation and also photolysis, both are negligible, absolutely orders of magnitude weaker at night than during the day.
Okay, makes sense.
So the corresponding time scales would increase by orders of magnitude due to the exponential dependence on time, and photodissociation is absent anyway because the source of ultraviolet photons is not there. The sun.
Great.
And Michael Poston has a hand up. Go ahead, Michael.
Okay.
Yeah, so I'm curious on that night side topic. If you thought about galactic cosmic rays, whether they or the secondary electrons they produce could actually lead to significant loss, or if they are going to be so small in magnitude that they also aren't significant to include. And then similar to those, there's some fancy magnetospheric effects that can happen during tail crossings that could happen on specific portions of the moon only on the night side. I think there's like, I forget what the people who actually know what they're talking about call it, backstreaming through the solar wind or through the magnetotail, or there's a flow that goes towards the Earth in the magnetotail that I forget what it's called.
Yeah, I must say we did not those things do not occur in our model, I must admit, and I would, because of course it's possible that protons are led to the moon by the magnetic field lines of the Earth. That's definitely possible. The question is how large is the corresponding flux? I have no idea, I must say, if it has a significant fraction of the daylight flux of solar wind protons. If that is the case, one has to take it into account. And if not, then one can more or less safely neglect it. So this is something that would need to be examined. So we have not done it.
Yeah, okay. And then a second kind of comment. I didn't catch if you considered the de Simon et al. Experiments for the I guess those were water rather than OH.
Water, yes.
But the surprise there was that the destruction rates seemed to increase as the ice layer got thinner, which is not something we see in any like gas phase results either, of course, because we don't have the surface involved. So I'm wondering if I'm curious to think about it. You said the lifetimes have to be longer than gas phase, but those results for a different but similar, well, I should be careful, a different molecule, but
Okay.
I wonder if those results have any relevance to this. I think that I would be surprised if UV photons can destroy hydroxyls that are not right at the vacuum interface. So I think, I wonder if the destruction of hydroxyl at the vacuum interface might actually be faster, consistent with the de Simon results, but then the depth that you considered in this model was deeper than what those results apply to. And maybe the destruction, if that hydroxyl is a couple molecular layers deep, is actually much, much, much slower.
Okay.
Thoughts on that? Did it make sense?
Okay, yeah, I see what you mean. The destruction rate of the hydroxyl is photodissociated by lunar, not by lunar, by solar ultraviolet radiation, and the penetration depth of ultraviolet radiation into the lunar surface is, one estimates, there are estimates of one wavelength, so a few hundred of nanometers, which means that if we assume such a thin, really thin layer of implanted OH, it might, so that means that the solar ultraviolet radiation can photodissociate implanted hydroxyl. That's what I would say. I don't know how one can compare, because I think in the paper you mentioned that has something to do with the cold environments and not warm environments like those that we have here. That's why I don't know how so many works look at volatiles in permanently shaded areas which are very cold and where different physical processes have a totally different relative importance than on the surface parts that are illuminated by the sun, which are warmer, and then suddenly temperature dependent processes become important that are totally absent in the shaded areas. And I must say, my knowledge is also limited to which extent these processes transition into each other when the surface gets illuminated.
Right. So when the UV photons are penetrating, they do go in potentially maybe 100 nanometers or more even.
That's it.
But when you break the OH, that hydrogen then has to escape. You know, it's several unit cells into the surface at that point. So there's actually a high rate of recombination back to OH if that hydrogen isn't able to diffuse away very quickly.
That's
so
right.
That's why I suspect that
That's right. That depends on the activation energy of the hydrogen, which is a parameter that we actually estimate with our model. And also this activation energy is usually assumed to follow an Arrhenius law and is again exponentially dependent on temperature. Yes, it is possible that hydrogen escapes very quickly from the surface after such a destruction by photodissociation. It may also react with an oxygen from lunar surface material. That can also happen, and in our model, we have included both processes. So it's difficult to tell which branch of that process is more important: escape to the exosphere or reaction with O. The problem is, once the hydrogen escapes to the exosphere, the probability that it leaves the moon forever is relatively high at those temperatures because the atomic weight of hydrogen is so small.
Yeah, and I think what can definitely be said is that you've got the effective lifetime of
Yes.
like the effective average lifetime of the hydroxyl.
Yes.
I definitely agree you've got that, even if the details at a molecular or atomic scale might be slightly different from how you modeled them. I think you do have the overall number from your results for sure.
Yes,
All right, thank you.
No, we definitely have not looked at individual subatomic processes, so it's rather sort of mean field approximation, and that's why we use this differential equation approach where only effective averages are computed, right? Absolutely. Okay.
All right, we have time for maybe one final question, if anyone wants to ask one. I'll wait a few seconds. They say you should always wait 10 seconds after asking for questions in a class. All right, if no one has one, I will ask one. And this is maybe for both of you, and it's a very general question, but based on all of your work so far, is there anything that maybe one or two things that you think might be particularly important in terms of either observations that could be made by future spacecraft or lab experiments or complementary kinds of modeling? But if are there maybe one or two things that you think would be particularly important in terms of either testing your models or providing input to your models?
Yeah, of course, what will be extremely important will be the 3-micron band depth measurements planned by Lunar Trailblazer, and to some extent there are also measurements that have been done with Chandrayaan-2, the IRS instrument on board of the Indian spacecraft, which have not been analyzed completely yet. And that will be definitely interesting also regarding not only the band depth, but also the band shape. And because only that will allow for a distinction to some extent between hydroxyl and water in the 3-micron range. And of course, it would be very good to have additional 6-micron band observations, because there we know it's water and not hydroxyl, in order to see if water has some kind of time of day dependent characteristics as well. And yeah, so the higher the accuracy, the better. Of course, one needs a lot of thermal modeling in order to evaluate that. So I think regarding those measurements, we are just at the beginning with the M-Cube data and the past spacecraft data. Regarding laboratory data, there are, for example, those measurements of absolute hydration in ppm by Lee and Millikan, which correlate them with Hapke's ESPET quantity. Yeah, the amount of data is limited though, so it would be good, although I know it's extremely difficult to measure hydration in the laboratory, but it would be good to have laboratory-based ground truth for the degree of hydration, because the absolute amount is in the literature is strongly varying, and I think in that point we are just at the beginning. So that would be an important point as well in order to be more certain about absolute abundances.
And from the thermal modeling perspective, I think it's important to look at a spectral region where the band goes up again, to have more constraints, because the thermal emission curve goes up and later goes down, and the more data you have, the more confident you can be about the thermal correction. I think future spacecrafts will look slightly behind the 3 micron band.
Awesome, excellent. All right, well, thank you all for sticking with us, and thank you, Kai and Christian, for spending your Tuesday evening with us.
It was a pleasure. Thank you for your invitation.
Of course, thank you so much. Yeah, I always think we should invite more of our European friends, but then the time zones become exponentially harder to. But yeah, but I'm so glad you could join, and thank you so much, and look forward to reading all of your many papers to come. And Kai, good luck for your defense and wrapping up your dissertation.
Okay, thank you very much, Parvati.
All right, thank you, everyone.
Okay,
See you again.
See you.
Bye.